Okay, last time we just covered this part, and actually it's about the relationship between the electric potential and the electric field. So actually we use the gradient operator to link between the electric field and the electric potential. And conversely, you can actually use a line integral to calculate the E field over a path, and then you know the uh, electric potential difference between the initial point and the final point. So, so it's nothing but a fundamental theorem of calculus for line integral. So next we consider a term called the electric potential energy. Electric potential energy. So here, potential energy of a system of charges particle is equal to the work need to assemble the system with the particles initial at rest and infinitely distant from each other. Which means that if two charged particles are placed infinite far away, then there are no energy stored between them because you can consider if there are two charged particles, there are some force either attract or repelling them. In this case, if you need to just fix them at a place, then you need to apply some work to make it stable because there are some force pushing them, so they will either go closer to each other or go farther uh, to each other. So in this case, there are some energy stored in this system. And actually, we can use this equation to quantify this energy stored in this two charge particle system. So it's quite similar to the previous field formula, like the F is K times Q1, Q2 over R squared. So here is just over R. Or you can imagine E is K times Q over R squared. And also V equals K times uh, Q1, Q2 over R. Q1, Q over R. Q over R. So in this case, it is Q1, Q2 over R. So there are totally four combinations because here it can be either Q1, Q2 or just only Q, and here it can be either R or R squared. So there are totally four combinations here. So we learn all of the four combinations. One is Coulomb's force, one is uh, electric field, and the other one is electric potential, and here comes the electric potential energy. So we need to denote it as U, capital U. So the total potential energy of a system particle is the sum of the potential energy for every particle of every pair of particles in the system. So here we consider there are n charged particles, and then we need to calculate the total energy stored here. So we need to do a summation. We have totally n particles, so we try to pick two, and then we calculate the energy stored there, and then we pick the other two. So if we have totally n particle and we randomly choose two, and then they do not repeat, so we can have totally NC2 combinations. And actually, the NC2, or maybe you can maybe you will write it like this, or some books it will write like this. But they are all the same. They are all the same. It is nothing but or generally NCR is nothing but n factorial r factorial n minus r factorial. So NC2 is nothing but n times n minus 1 over 2. So do you know how to calculate maybe 1/2 factorial? Not actually, because actually we can generalize the factorial into a gamma function. The gamma function, I'm not sure, maybe you will not learn it in graduate. I'm not sure. Yeah, actually, the gamma function can be generalized into a gamma function. So in this case, gamma function n minus n plus 1 will be equals to n factorial when n is integer. Actually, you don't need to know this. I just tell you about it. And actually, this one is somehow like, I'm not sure whether I can remember it correctly. It is something like this. E to the minus, no, it is somehow like t to the n plus 1 e to the minus t, somehow like this. Somehow like this. So it can be differentiable for infinite times. And then when n is integer, it is a shift version of the factorial function. You can find it on Wikipedia, the gamma function. If you are interested. So you may know that I'm not really sure. So 1/2 factorial is somehow like the square root of pi. So actually here we calculate the electric potential energy, and so for this summation, you can just imagine like this. Suppose we have maybe three particles. So you can have I and J like this, and then suppose we have 3 particles. So it is somehow like this. So I equals to J is not applied here, and we may choose this one, and this one and this one is repeated. So we don't choose these 3. So we have this one, and this one. So we may have I equals to 2, J equals to 1, I equals to 3, J equals to 1, and I equals to 3, J equals to 2. Or maybe you can choose these 3 rather than that 3. That is actually the same, because R1, Rij and Rji is the same. So we consider I is not equal to J. So we just skip the diagonal line. So for 3, we have the 3, because it is 3 times 2 over 2. So there are only 3. And if there are 4 particles, there will be 4 times 3 over 2, which is 6. So you have 3, 2, 1, something like this. Okay, so we have a sample problem. So 3-point charge held in a fixed position by force that are not shown. What is the electric potential energy U of this system of charge? Assume that D equals to 12 centimeter, Q1 equals to positive Q, Q2 minus 4Q, Q3 plus 2Q, and in which Q equals to 150 nanocoulomb. Okay. So calculating the scalar sum is simple. We don't really need to care about the direction. So U will be U12 plus U23 U23 plus U31. Okay, so it's nothing but K times Q1, Q2 over D, or the R1, R12, R23, R31 are all D. So we can just write D here, and we have Q2, Q3 over D plus Q3, Q1 over D. So it is nothing but 8.99 times 10 to 9 over D is 12 centimeter, which is 0.12. Q1 is 1. Q2 is minus 4. Q2 minus 4. Q3 plus 2. Q3 plus 2. And then 1. And then times 150 nano. So the answer would be minus 1.7 times 10 to minus 2J. Any questions? Okay. So we have another one. So you can see not a moon, it is a gold nuclear. And this is alpha particle. Alpha particle is 2 proton and 2 neutron. So it should be somehow like a helium. Yeah, helium is has a elementary number of 2, so it has 2 proton and 2 neutron. So we call it a alpha particle. Maybe it has some relationship with the nuclear reaction, so we may call some particle the alpha particle and another one beta particle, something like this. Yeah. So an alpha particle moves into a stationary gold atom. So it is much larger and much heavier. Passing through the electron region that surround the gold nucleus like a shell headed directly toward the nucleus. The alpha particle slows until momentary stop when its center is at radius r equals to 9.23 femtometer. Femto is 10 to minus 15 meter from the nuclear center. then it moves back along its incoming path. Because the gold nucleus is much more massive than the alpha particle, we can assume the gold particle does not move. So it's somehow like the conservation of momentum and conservation of mechanical energy. So what was the kinetic energy Ki of the alpha particle when it was initially far away, hence external to the gold atom? Assume that the only force acting between the alpha particle is and the gold nucleus is the electrostatic Coulomb force. So it's somehow like they correlate with each other, but actually not, because they are both positive charge. They are both positive charge. So actually, when this alpha particle try to move closer to this gold nucleus, then it will slow down, and until some point it will stop and then go back. So they actually don't correlate with each other, but it's somehow like that. So in this case, we try to calculate alpha particle is 2p2n, gold particle 79p, 118n. So we try to use the conservation of mechanical energy, which is Ki plus Ui, which is the kinetic energy, plus the potential energy, equals to the final value. So initially they are far away. So the potential energy should be zero. And for the final state, kinetic energy should be zero, because when they come just very close to each other, this is actually stop and then it try to go back. So at this moment, the velocity for the alpha particle is the velocity is zero. So the kinetic energy is also zero. So in this case, we have the Ki, the initial kinetic energy, which is what we want to find, equals to UF. So UF is nothing but 1 over 4 pi epsilon naught times 2 times 79. Because the alpha particle has two positive elementary charge, 2 proton, and the gold atom has 79. So 2 times 79 times 1.6 times 10 to minus 19 square over R. R is 9.23 femto. So 9.23 times 10 to minus 15. And actually this one is 8.99 times 10 to 9. So it would be 3.94 times 10 to minus 12 joules. Or sometimes we will try to use another unit to express this one. Actually, we can just divide this 3.94 times 10 to minus 12 by the elementary charge amount. And it will be 24.6, and then the unit we'll call it mega EV. Actually EV. Capital M means 10 to the 6 power. 10 to the 6 power. So if you just divide this one, this is the energy in joule divided by the elementary charge amount, then this one has a SI unit, EV. It is somehow like you use a 1 volt voltage potential to accelerate a electron. Then it will have this kind of energy stored in the electron. So the SI unit already tells you that it is related to the electron and the volt So here we talk about this one is somehow like a story. So the potential of a charge isolated conductor. So an excessive charge placed on an isolated conductor will distribute itself on the surface of the conductor, so that all points of the conductor, whether on the surface or inside, come to the same potential. This is true even if the conductor has an internal cavity and even if that cavity contains a net charge. So this means that here we show a car, and then there is a lightning hit on the car, and then a man is inside, but the man is safe because for the whole car it is the same electric potential. So so there will be no current going through the person, so he will be safe. It's somehow like when you have somehow like if you have the tile table on the street or in the rural area, then suppose the bird is stand here, then you will not die because actually the potential energy will go up and down, so there will be no current going through the bird, and the bird will be safe to just stand on the power cable. So here on the left side, we also show that we can consider using the Gauss law. We can consider using the Gauss law as you can imagine a imaginary Gauss surface inside the car, and there should be no charge, and there will be no E field. There will be no E field, and outside of the car, if there are some charges, then there will be some E field decaying with respect to the distance. And if you just integrate from 0 to infinity, then you consider here it is going flat, and then actually when you integrate the E, you need to add a negative sign. So this is positive. So when you integrate this part, it will going down. So that this one is like you use the star going from the bottom to the top, And if you want to go from top to the bottom, you use the derivative. You use the derivative. So when you take the derivative here, the voltage, the electric potential are the same between 0 and 1 meter. So the slope here is 0. So you can see here the electric field is 0 here. And then this will decrease. This one is decreased. So the slope here is negative. The slope here is negative, somehow like this, or like this here. So the slope here is negative, and then we have another negative sign. So this is positive here. And you can see that the slope here is larger, the slope here is smaller. So you can see that the electric field here is larger, and the electric field here is smaller, somehow like this. So far we have learned a lot of variable, electric, the Coulomb's force, the electric field, electric potential energy. So actually we can connecting them like this. So for the upper row, we have electrostatic force, and the electric field. Both of them are vectors. And on the lower row, there are potential energy and electric potential. So actually, they are scalar. So some mentality of the electromagnetic sum is somehow like we try to find the electric potential, which is supposed to be easier to find, and then we can use the gradient operator to derive the electric field by the electric potential. And then there are some definition and calculation between them. So for the Coulomb's force and the electric field, we learned it in chapter 22 at the very beginning of the chapter 22. So they are just proportional to each other. So you just multiply the E field by the test charge, and then it will be electrostatic force. And between the potential energy and the electric potential, you learned it just now. So they are just multiplying Q0 to the electric potential, and then you become U. Or actually, you can just use the gradient operator, or just take the derivative. And then no, not derivative here. So they are just multiplying Q0. They are just proportional to each other. And here, the electrostatic force and the potential energy. So they are connecting by this line integral. So you integrate the electrostatic force over a path, and then you put a minus sign, then it will be the potential energy. Or on the other way around, you can just take the gradient to the potential energy, and then take the minus sign, then it will be Coulomb's force. Or on the right side, the E field and the electric potential has a similar relationship between them. So this graph is quite beautiful, I think. So we have additional example. And so far, any questions? No questions. So here, I'm not sure. So here we have a thin we have a thin plastic rod length L equals 13.5 EX centimeter and uniform charge. In terms of distance D, find the expression for the electric potential at point P1. Find the electric potential. So actually, we can just use the integration, and we can separate this rod into many small segments, infinite source segment, and maybe we can call this part dx, and the total charge is Q, and then there are actually dq on this part. So dv is nothing but k times dq over d plus x, because we need to consider the distance between this point and this small segment. So actually the x-axis is nothing but x, and the total distance will be d plus this x. This one is x. So you add d and x together, so that it will become d plus x. And actually we only need to integrate x from 0 to capital L. So this one is always positive. This one is always positive. So this one is good enough. So we can consider dq is lambda dx over d plus x. So v is integration of dv, which is k lambda integration from 0 to capital L dx d plus x. So you can just simply add plus d here, because d is nothing but a constant. So dx plus d is nothing but dx. So here we have k lambda. So this one is nothing but log d plus x, and then we substitute ln 0 to there, so it will be nothing but ln d plus l over d. So we substitute the number. K is and actually we can multiply L and divide by L, because lambda L is Q. Q is lambda L. Q is lambda L. So we have lambda L. This one is Q. So K is 8.99 times 10 to 9, and then Q is 43.6 times 10 to minus 15. L is 13.5. centimeter. So we should be 0.135. This one shouldn't be EX here. And ln d plus L. D is D is what? We don't know what is D, so we just keep it a variable. So 0.135 over D, somehow like this. And we may just calculate it a bit. So it becomes 2.9 times 10 to, ouch, 2.9 times 10 to minus 3 volts ln 1 plus 0.135 over D. This is meter. So their expression was somehow like this. So next one, substitute variable x for D and find the expression for the magnitude of the Ex of the electric field at P1. So it tells you to just substitute this D into X. So it is nothing special. So we will have V equals to this one 2.9 times 10 to minus 3, we call it V0. So here we have V equals V0 ln 1 plus 0.135 meter over x, because it's us to substitute variable x for D. Then we can calculate Ex, which is minus dV dx. So it will become minus V0 and then 1 plus 0.135 meter over x. And then the chain rule, which is 0.135 minus I, and then x squared. So it will be somehow like minus V0 0.135 over 0.135 plus x times x, which is nothing but some algebraic calculation, because x squared is here, so you can put it here, and then you just cancel one of it. And actually, you can just replace V0 as 2.9 times 10 to minus 3. 2.9 times 10 to minus 3. So it finally becomes 3.92 times 10 to minus 4 over 0.135 plus x times x. And this is V over m. And it asks you that what is the direction of Ex What is the direction of EX relative to the positive direction of the x-axis? Opposite direction. I forgot a minus sign here. I forgot a minus sign here. A minus sign here. So for part C, which is nothing but EX is negative, is smaller than 0, is negative. So it points to the negative x-axis. And it is very trivial because this is a positive rod. So even without calculation, you can imagine the if you points to this side, somehow like this. So next, a flint plastic rod of length L. What is the value? Oh, so wow, it should be P2 here. So for this one, we calculate the EX here. Is it or not? P1, what is the value? No. No, not that difficult. We still, it is for other question. You can, if you have the textbook, you can see that is for other question. So actually, we still calculate the EX here. So it is nothing special. We just substitute x equals to d equals to 6.2 centimeter into this expression, into the previous expression. So we have EX is nothing but minus 3.92 times 10 to minus 4 over 0.135 plus x is 0.062 and this one 0.062. So the answer will be so we just consider the magnitude. So it is nothing but 0.0321 Newton per coulomb. Or you can write it as 32.1 milli-Newton per coulomb. Or if you like, you can use V over M. Both are correct. And this is for D. And part E, from the symmetric, determine EY at P1, which is very trivial. EY is nothing but 0. So we still have another additional example there. Okay. So a plastic wad has been bent into a circle radius r equals to r equals to 8.2 centimeter. it has a charge Q1 uniformly distributed along 1/4 of the circumferences, and a charge Q2 equals to -6 Q1 uniformly distributed along the rest of the circumferences. With V equals to 0 at infinity, what is the electric potential at center C of the circle? So this is pretty easy. Because you just only need to consider the potential, which is nothing but a scalar. So you don't really need the integration because it is a circle. So all the distance from every part of the circle to the center is the same, which is nothing but capital R, So we can just calculate. VC is K times Q1 over capital R, and then plus Q2, which is nothing but -6 Q1 -6 Q1 over R, so which will be minus 5K Q1 over R. So well, yeah. So for the next one, what is the electric potential at point P on the central axis of the circle distance d from the center? So we consider the electric potential at this point rather than the center, but actually this is nothing but you draw a perpendicular line with respect to this circle, and then it has a distance capital D. So here this is R. So R is nothing but D squared plus R squared quantity square root. So we have R is D squared plus R squared, then take the square root. So R is D is 6.71 square plus 8.2 square, take the square root. So this is 10.6 centimeter. And VP would be actually minus 5Q1 K over small r. So we can well, actually for the previous one I forgot to substitute the number. So actually this one should be minus 5 times K is 8.99 times 10 to 9, and then Q1 is 1.2 times 10 to minus 12 over R is 0.082. So this voltage would be minus 2.3 volts. And then for this one, it should be minus 5 times 1.2 times 10 to minus 12 times 8.99 times 10 to 9 over 10.6 centimeter, which is 0.106 meter. So this one would be minus 1.78 volts. So any questions? Okay, let's finish the last one, and then we will have a short break. We'll have a 10 minutes break. And so here we have a plastic disc of radius r is charged on one side with a uniform surface charge density sigma. And then 3 quadrants of the disc are removed. What is the potential due to the remaining quadrant at point P, which is on the central axis of the original disc at distance d? So it's somehow similar to the previous case. And actually, we can make use of this one. For this one, it is somehow like if we have a full disk, we don't have this 1/4 factor in the front. We only have that part, but we consider the electric potential, which is a scalar. So if we just remove 3/4 of the disk, then the electric potential at this point regarding to this quadrant will be 1/4 to the whole plate. So in this case, we just substitute all the number. Just substitute all the numbers, and then we have 4 times 2, which is 8, and then epsilon 0 is 8.85 times 10 to minus 12, and then sigma is 7.73 times 10 to minus 15, and then this one z is this capital D. Capital D is 0.259 square plus r square. R is 64 centimeter, which is 0.64 square. Take the square roots, and then we minus z, which is capital D, which is minus 0.259. So the answer will be 4.71 times 10 to minus 5 volts.